Bismillahirrahmanirrahim. In this video, we are going to be discussing about relational database designs and functional dependencies. So just to recall what we have done so far and to analyze where we are at this time in the course, I have the following slide. So this gives us a very good idea about what we have done. So we started our database design by looking at textual data, trying to find nouns and trying to find verbs from that, trying to make tables and their attributes, and then from that we went on, that was the conceptual model, and then we went on to the logical model where the tables and were transformed into logical tables, where relationships were transformed into new tables. We figured out how to deal with one-to-one and one-to-many relationships, many-to-many relationship. We went for the extended ER model. We looked at inheritance, and we ended up with a logical relational model. So the logical relational model is a very fair model, but it has certain limitations to it. Primarily, there are limitations regarding the insertion, deletion, and updation of data in that model. So in this part of the design, we are going to look at what is the next thing we do to a logical model to make it what is known as the normalized schema. So in particular, we are going to be looking at a database normalization. So the tables that we created are now going to be normalized so as to facilitate insertion, deletion, and updation. And this is done by minimizing the replication of data, having the data designed in such a way so that there is least amount of dependencies between one table and another. That specifically means what we have been saying in this course, one fact, one table. So we don't distribute facts across different tables, and we don't clutter different things in the same table. So this lecture is basically a preamble for the normalization. We are going to look at the problems that we encounter using the insertion, deletion, and updation. And we are also going to look at what is known as functional dependencies, and this will form the background for the next topic, which is the actual part of the design of the analysis and design of the database, which is called normalization, and that will be covered in the next two subsequent lectures. So here are the focus of this lecture. So the problem with the relational database design is that even though we have formed the tables, we have tried to resolve the relationships and the attributes, there are still issues about functional dependencies, which I'll come to in a moment. And to do that, we have, instead of the 10 commandments, we have only 4 commandments here. We have been talking about this informally throughout the class, and the 4 commandments that we have is that thou shalt commit no redundancy of facts. So a fact should not be repeated, and this translates to one attribute, one table, except of course when that attribute is used as a primary key or a foreign key, in which case it's more of a reference rather than a replication. But otherwise, one fact or one attribute must only occur in one table. So that's the first thing we have to consider. The second one is thou shalt clutter no facts, and this is translated as different information, different tables. So for instance, if you are storing the data about an employee, and then the employee name and the department for which he or she is working, and what's the name of the department. Now these are two things. The name of the employee, maybe the salary, the birth date, or the qualification. These are things that are specifically to an employee, and they should be in the employee table. And what is the department, what is the size of the department, what's the name of the manager of the department. Those are specific things that are related to the department, and those two things should never be in the same table. They should be always in different tables. The third thing here is thou shalt preserve information. So there should be no deletion or merger of attributes. All the information given should be preserved. And the fourth and final one is thou shalt preserve functional dependencies. Now this video is about functional dependencies. We are going to look at what functional dependencies are in detail in the rest of this video. In summary, what this means is that if I have something, this A and B are attributes. So if attribute A depends or determines attribute B and attribute B determines attribute C, I am not to remove B and make a direct dependency that A determines C. So B was an intermediate attribute that was functionally that had functional dependencies. So I am not to remove those kind of things. So these are the 4 commandments and these are the 4 guidelines that we will be using during the normalization process. Let's look at it in more detail. So here's one example, and the question at the top you can see is this a good design? So what we have here is that we have the employee table, and the employee table has the employee name, the social security number, the birth date, the address, and the department number. And then the department has the department name and department number and the manager social security number. And then we have department location and then project and who works on which project. So you can see here that all the data is well separated. The employee table has information only about the employee. So this is the name of the employee, the birth date of the employee, the address of the employee. And while this might look as duplication, D number here and D number here, this is basically primary key, foreign key relationship. So that's an exception. Otherwise, there is no duplication of any fact. There is nothing that is stored. For instance, which project this employee is working on is not in the employee table, but we have a separate table for that, works on, which states which employee is working on which project and for how many hours. Similarly, which department is located where. So these things are well separated in the database. So the question again, is it a good design? Yes, it's an excellent design. And it's an excellent design because one fact, one table, every table is independent. It only stores facts about the employee or the department or the project. There are no tables that have multiple facts in that. There is no fact that's repeated in multiple tables. The functional dependencies, we haven't covered that in detail yet, but they are preserved and no information is lost. So this is a good design. Compare this to a bad design. A bad design is in which the employee and department are merged into a single table. So here we can see that the employee name and the department name and the department manager and department number, they are all in the same table. So this is a case where we have multiple facts in a single table, and this is never a good design. Is there going to be a redundancy? Yes, there is going to be redundancy. For every department, the employee name is repeated, the birth date is repeated. For if I have an employee working on a project, so if I am an employee and I'm working on 2 or 3 projects, it means my name is going to be repeated. It means the location where I work is going to be repeated. So yes, there is repetition here. So there is redundancy. One fact, one place. No, this table has information about both the employees and the department. So this is not one fact, one place. Are there insert, delete, and update anomalies? Yes, there are. If I want to insert something, if I insert an employee here, I must know the department that that employee is working on. If I make a new department, I cannot insert the name of the department unless there is already an employee assigned to that department, because SSN here is a primary key. So I cannot add a new department unless there is already an employee working in that department. So there are insertion problems. Similarly with deletion problem, if I remove the last employee working in a department, it means I am essentially also removing the department from the database. And update is if I happen to go on another project or somebody is replacing me, it means I'm not just going to have one entry, but all my employee name, the project name, and the project location, these things will be repeated. So there is a problem with redundancy, there is a problem with one fact being at one place, and there are problems with insert, delete, and update. So this is a really, really bad design. Next, we look at something which is called the spurious tuples. And what is a spurious tuple? Let's look at this example. So in this case, it's the same table from the previous slide. We have the social security number, we have the project number, we have the hours worked, the employee name, the project name, and the project location. So just let's remember the first data entry here, because we'll be using that. So let's look at this. The SSN is 1, 2, 3, 4, 5, 6, 7, 8, 9. This person has worked 32.5 hours. The name of that person is John Smith, and he has worked at this location, Bel Air. So if I split this data, so because there is too many facts in one table, I can decide, let me split this table into two. And the way I split it is that employee name and project location is in one table, and the employees and the projects are in a separate table. So what I have done is, what I've done here is that I have separated it, but the question to be asked is whether this is a good separation or not. And the way to recognize is that whether it's a good separation or not is that once I want to merge it and create back this original table, can I be able to do it? And the answer is I cannot be able to do it because of the way I have split this table. Let's look at the split here. So in this case, the employee and the locations are in this table, and the employee and projects are in the other table. So if I want to join them, I have to make a natural join. How do I make a natural join? What's common between here? So the project location is common. So if I make a natural join, it means I am going to write select asterisk from employee locations, employee projects, and that's it, because I don't need a where clause. It's a natural join. It's automatically going to make a join on P location, because that is common between the two tables. And if I do that, this is the result I get. And if you remember, I asked you to remember this. I said 1, 2, 3, 4, 5, 6, 7, 8, 9, working 32.5 hours on project X, and the name of that person is John Smith, and he's working in Bel Air. Now if we join it again, because of the way this is being done, we are going to end up with some problems. Why? Look at this row. So look at this row. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, this is right. This is right. What's the name of the person here? The name of the person has changed. So I have this additional row inserted which does not exist in the original data. The original data before I split it. It does not occur here. So because it doesn't occur here, this is a bogus, or what we call as a spurious tuple, a spurious row. It should not be there. And all these rows that are mentioned here with an asterisk, they're all spurious rows. It means they should not be there. So this is the problem with a bad splitting. So when you are splitting a table between two or more tables, you have to take care of these kind of things. So, and this is one of the major things that we need to do to make a design from a simple logical design into a design that is normalized. A normalized design is one in which all these kind of problems are eliminated. So let's come back to the guidelines for the 4 commandments. We have the 4 commandments, what should happen and what should not happen. And here we are going to give a set of guidelines that will ensure that the 4 commandments that we discussed earlier are ensured. So the first guideline is that each tuple in relation should represent one entity or one relationship instance. Each attributes of different entities should not be mixed in the same relation. Only foreign keys should be used to refer to other entities. There should be no duplication of any attribute in 2 tables except when it's a primary key and foreign key. Entities and relationship attributes should be kept apart as much as possible. So the tables and the relationship between the attribute, they should be kept apart as much as possible. The second guideline is that mixing attributes of multiple entries may cause problems. This may result in redundant storage. We saw that, which is going to cause wastage of the storage facility and result in anomalies. We have already seen that in the previous 2-3 slides. The third guideline is that there should be as few rows in the table with null values as possible. This is particularly important when you are using the extended ER model, when you are having the is-a relationship, when you are having inheritance. And we saw four ways in which we can make a logical table out of extended ER diagram. And one of them said that, if you can make a separate table, and if one does not occur, just put the null values there. And this guideline here is telling me that there should be as few rows in a table with null values as possible. If such a thing occurs, if it's inevitable, separate attributes that are frequently null and place them in another table. So if I have one table, if I have a table like this, and there are different attributes, so A1, A2, and so on up to AN, there are different attributes. So let's assume this is my primary key. A1 is my primary key, and some, let me say AP here. This has a lot of null values. So a lot of null values are occurring. What I can do here is that I can remove this attribute from this table, make a new table which have only two attributes. I'm going to take the primary key here. So this is going to be A1, and then I'm going to take AP. So all those null values, they will only, so if it's a null, you don't have an entry here. If it's not null, you have an entry here. So you remove this column, and then you shift it to another table. In this way, you are avoiding all the null values. And the fourth and final guideline is that all tables in a design should satisfy what is known as the lossless join condition. The lossless join condition is what we just saw with the spurious tuples. It means that if a table is split and then rejoined, there should not be an additional new things, and existing data should not be lost. So no two or more tables should result in spurious tuples when doing a natural join. So this is the fourth guideline when we are designing the database, the logical database. So if we keep these four guidelines, hopefully we are going to minimize the three anomalies that we have, the insert, update, and delete anomalies that we have. We are going to eliminate the lossless join or the spurious tuples and several other problems that we encounter with logical design. Another thing we need to talk about, which is again going to be used for the normalization. As I said, this is a preamble for the next lecture, which is about the next 2 or 3 lectures, which are about normalization. So in this lecture, we are going to understand the fundamental problems and how we can identify the relationship between attributes so that they can be used during normalization to ensure that our database design is consistent and robust. So apart from the 4 commandments and the 4 guidelines we have seen here in the problem of spurious tuples, there is something called functional dependency. A functional dependency is a constraint on the contents of a relation. So the contents of a table. A functional dependency specifies that values for one set of attribute determines the value for another set of attributes. So what I'm saying here is that if I have a table, then one attribute is dependent on another attribute. For instance, if you look at this table, so this loan info schema, this is the name of the table, and the schema of that table, or the attributes of that table are customer number and loan number, which form together the composite key. And then there are 2 additional attributes, branch name and amount. So what are the functional dependencies? If I know the loan number, I can determine the amount. So the amount entry here is dependent on the loan number. I can write it like this. So loan number here determines the amount. And then the loan number also determines the branch name. So if I know the loan number, I can figure out from which branch this loan was given. What are some of the non-applicable functional dependencies? So this may look logical, but they are not. If I say loan number determines customer name, no, it doesn't. And if I say customer name determines the amount, No, it doesn't. So this here, it may look logical. You know, I can look at the customer and I can figure out what's the amount of this person has taken. Why is loan number a determinant of amount and customer is not a determinant of amount? And the reason is that if I have one customer, let's say myself, and I have loan number 001, and the amount of loan I took was 100,000, and I went on to another bank or another branch, I took out another loan, and that was of 200,000. So my name here is not capable of determining the loan amount I took. However, the loan number is a good determinant. So if you say what is the amount of loan taken by loan number 001, we have only one answer, which is 100,000. However, if I say what's the loan amount taken by this person, it can be this or it can be this. So I'm not sure whether you're talking about this or you're talking about this. So that's why customer name is not a determinant of the amount, but loan number is a determinant of the amount. So there are some, not all possible dependencies are functional dependencies. A functional dependency means that the attribute on the right side can be determined by the attribute on the left side, just as we saw in this example. So some other examples of functional dependencies. So for instance, I have the grade schema. We have the student ID, the name, the course ID, and the grade. Now the name is solely dependent on the ID of the student. If I know your reg number, I know your name. But if I know your reg number, I don't know your grade unless you give me the additional information of which course I am talking about. So a student ID determines name, and the combination of student ID and course ID determines the grade. However, student ID alone cannot determine the grade, and the grade alone cannot determine the course ID. So these are functional dependencies, and these are not functional dependencies. Note that there is also always a trivial dependency, which means that I say student ID always determine student ID. This is a trivial thing. The one on the left hand side and the right hand side are equal, or grade determines grade. So these are trivial dependencies. They are always true, but we're not interested in them because they give us no additional information that we need. So as an exercise, I would like that you try for your own practice to find out all the functional dependencies. These are just some of the functional dependencies. You can list all the dependencies, all possible combinations, and then figure out which one are functional dependencies and which one are not functional dependencies. And you can ask me that during the question hour time, or you can show me, and then if there's anything, if it's right, I will tell you it's right. If there's anything wrong, I'll point out the mistake during that time. Let's look at the formal definition of that. So we tend to formalize a lot of things. We tend to bring in mathematics in a lot of things, because that means that we are not going to misinterpret anything, because mathematics is a very clear language. We don't misinterpret anything. Formal definition: let R be a relational schema where alpha is a subset of R and beta is a subset of R. So the functional dependencies alpha determines beta is said to hold on R, the relation R, the relation schema R, if and only if for any legal relations. So the relational schema is the complete model, and the relation R is the table. So any table of R, of the schema R, capital R, a small r is the name of is the table, and capital R is the schema. So this is alpha determines beta is said to hold on R if and only if all the tables that belong to this capital R schema, whenever any two tuples, rows T1 and T2 of this table R, agree on attribute alpha, they also agree on the attribute beta. So T of alpha equal to T2 of alpha, and T1 of beta equal to T2 of beta. So if this holds for all possible values, then I will say that this functional dependency holds. For instance, in the last example, if I have the loan number and the amount, so if I take loan number 001 and the amount happened to be 100,000 in any one table. So this is table A, and then we have another table B. Then the same thing must hold true, and for any two, if this row is T1 and I have another row T2, then 0, 0, 2 should also determine this value. So this has to hold for all cases. If this is true for all T1, T2, then I'm going to say that this is my alpha, so lone number here, this was my alpha, and amount here, this was my beta. So alpha determines beta. So this is the formal definition of a functional dependency. We say that F holds on R if all legal relations on R satisfy the set of conditions. This F is imposed or enforced on R. There's also a case where we say that if a relation R is legal under F of functional dependencies, we say that R satisfies F. And this may be true for the data, but it may or may not be true for all the cases. For instance, if I say that this is my first name and last name, so I have first name and last name, and my first name is this and this, and then I have another entry here. So if this is the table, then does it hold that F name determines last name? It is satisfied, yes. For all the cases, if I know the first name, I will be able to determine the last name. So this is currently satisfied, but may not be imposed or enforced. What this means is, in this table, it is satisfied. However, I can always come up with another example where I have maybe this, and who else? Okay, we have the Science and Technology Minister Fawad Chaudhary. So in this case, this fails. So up till this point, it was true. However, it was legal, but it was not imposed or it was not binding, because there's always a case where this may not be true. If this entry does not exist, then this is legal and this is currently satisfied. So that's the difference between a functional dependency being enforced, and so in this case, there can never be a row which does not satisfy this condition. So in this case, it is enforced or it holds. In this case, it is just currently satisfied, because you can always have an entry like this which will disprove it. Let's look at a few more examples. So in this case, we have the student and department. So we have the student number, the department name, the department head, the course name, and the grade. What are the functional dependencies? So if I know the student number and the course name, I can be able to find the grade. So this does not mean that student number determines the course number. No, because there is no arrow here. It means that this and this combined determines grade, because there is arrow. This is the determined attribute, and these two are the determining attributes. So these two are the left hand side, which we can see here. And then we have that the student number, if I know the reg number of the student number, I can, or the serial number, whatever this S number is, I can determine the department name. If I know the department name, I can determine the department head. Just knowing this, I cannot determine directly the department head, even though, as we will see later on, this is a transitive dependencies. A can define B and B can then define C. It means A can define C. We'll look at that in the next few slides. But given the information I have here, we can say that these are the functional dependencies that exist. Let's look at another example. In this case, it's the same example from the previous few slides. We have the employee name, the SSN, the birth date, the address, the department number, department name, and the department manager social security number. So here we have the social security number is determining the employee name, the birth date, the address, and the department that employee is working. And the department number determines the department name and the manager. And same goes for the employee project. You can see all the functional dependencies, the legal functional dependencies listed here. So FD1 is the first functional dependency, the second one, and the third one. And these functional dependencies will form the backbone of the normalization, which we'll consider in the next 2 lectures. So it's important that you get these functional dependencies right. So we have this, we can show it either diagram. This is called a dependency diagram. We can list it like this, or we can show it in this diagram, and this is called a dependency diagram. And we have a third example here, which is again the example of an employee. So we can see that an employee ID here is determining the name, the department number, and the salary. So this is a good example, and what I'm trying to show here is that this is how our tables should look like. When, if you recall, we said what is a good design and what is a bad design. So the primary key here is determining all the other attributes. This is a good design. This is how the table should look like. And this here is another example. It works because we have a composite key over here. So this is determining these 3 attributes, and the combination of this is determining this attribute. So far this is okay, but when we talk about normalization, we will have a question mark about this, whether to leave it like this or to split it into 2 tables. But that we'll talk about when we talk about normalization. Here the important thing is to say that this is the ideal thing we like. It's not saying that we are never going to tolerate this, but this is ideally what we want. If we have this, we are going to go through the normalization process and then determine whether to leave it as it is or to split it into 2 tables. So some of the properties of functional dependencies are that they are there's a reflexivity there. So if B is a subset of A, then A implies B also means that A implies A. In other words, if the street name and street address combined gives me the street name, so this street name is also already part of the street name, I can deduce that street name give me the street name. This is trivial, but this is a reflexivity property of functional dependencies. The next one is augmentation. If I have A implies B, I can add C here and I can add C here without having any major consequences. So if I say that the student ID determines the student name, so the student ID and address determines the name and address. There is nothing wrong with that. I have the address determining the address, and already I had the student ID determining the name. So this works fine. So I can augment it. If I had A implies B, I can add C on both sides. So CA implies CB. Then we have transitivity, which means that if A implies B and then B implies C, then A implies C. So if student ID implies the project name and the project name implies the credits, then we can say that the student ID implies the credits. So this is also possible. And the final set of properties for functional dependency is addition or union. So if I have A implies B and A implies C, then I can say A implies the combination of B and C. For instance, if the employee ID can determine the employee name and the ID can also determine the qualification, then I can say in one single dependency, functional dependency, that employee ID can determine the combination of the name and qualification of that employee. And the projectivity or decomposition means that if A implies CB, then I can decompose this part and say A implies B and A implies C individually. So basically this and this are opposite of each other. Here I had A implies B and A implies C, and I merged them together to form A implies CB, and here I had A implies CB, and I can decompose it to get the original parts. Then we have the pseudo transitivity. It means A implies B, then C and CB implies D. Then I can say that AC implies D, and the reason being is that because A implies B, and so D can be replaced by A. If I have A, then it implies B. If I had A, I can always bring B here, which will give me the CB, and which will implies D. So I can do that. So these are the 6 properties of functional dependency, and they are very useful for what we calculate the closure of the set of functional dependency. What is the closure of set of functional dependency? It means that if I have something like this, A implies B and B implies C, and then I can infer A implies C. So if I had just A implies B and then B implies C, this together with all that I can infer from this, so will form F plus. This will form the closure of S. So the set of all functional dependencies logically implied by F is the closure of F, and it is denoted by F plus. It means this. So if I had A implies B and B implies C, and F plus will include A implies B, B implies C, and also A implies C. This is the derived one. So everything will be included. This is the closure, and if there is anything else possible, that will also be included. So this was given to me, this was given, and this was deduced, and the combination of the given and the deduced together will form the F plus. So I need to put a bigger bracket over here. And we can use these possible properties that we saw in the last 2 slides to determine the F plus, and these rules should be sound. It means that they should actually hold and they should be complete. So this is the final example we have for this lecture, and if we have R, which has A, B, C and G, H, I, and my functional dependencies was A implies B, A implies C, and CG implies H, and CG implies I, and then B implies H, some of the members of F plus. So all of these are included in F plus. Apart from that, since I have A implies B and A implies C, I can have something like A implies CB, and then I have A implies B and B implies H. I can have something like A implies H, and this and all others are going to be included in the closure of this. So these are some of them. There are going to be others as well. So this is with the functional dependencies. This is a summary of the axioms. They are called the Armstrong axiom, and we use them: the reflexivity, the augmentation, the transitivity, the addition or the union, the decomposition, and the pseudo transitivity. However, it's important to note that A, B implies C. This means that the combination of A and B implies C, and it does not mean that A implies C or B implies C. For instance, we said that student and course ID, the combination of student ID and course ID can determine the grade. However, student ID alone cannot determine the grade, because I don't know which course you're talking about, and the course ID can't determine the grade either, because I don't know which student you're talking about. So you should not make this mistake. This is a common mistake that people make. So you should remember that this does not hold true. And I think you might have done this in discrete mathematics as well, if you have done that course. So that's it for this lecture. If you have any questions, you can either ask me by email you can post it on the Microsoft Teams page, or you can ask me during the question answer session, or you can even ask it in the comment section of the YouTube video where I'm going to be uploading this. So that's it. I hope it's not very difficult, but you need to maybe look at it once or twice to get this idea, because it's very important to know about the problems about insertion, deletion, updation, and about functional dependencies. This will form the basis for the normalization that we'll do in the next two lectures. And the normalization itself is done after doing the normal logical design process, and it's done to eliminate the problem that still remains when we make tables and when we convert relationships into one to many, many to many. When we convert all these, there are still some problems that remain, and we eliminate those problems using the normalization. And to do that, we use these concepts that we studied in this video. So that's it. Thank you very much.